Hello everyone, I am Li Qina from the Electronics and Information Engineering Teaching and Research section at Wuzhou University, and welcome you to this mini lecture. In the previous sections, we studied the definition and properties of the Z transform. Today, we will move on to section 6.5, Z Transform Inversion. Given Fc and its region of convergence, ROC, finding the original sequence Fk is called the inverse Z transform. As shown in the formula below, the inverse Z transform is defined using a contour integral, where the integration path C is a closed counterclockwise contour inside the ROC of Fc that encloses the origin, as illustrated in the figure on the right. There are several methods to compute the inverse Z transform: the power series, long division method, the partial fraction expansion method, and the residue method. In this section, we will focus on the residue method and the partial fraction expansion method, starting with the partial fraction expansion method. Similar to the procedure used in the partial fraction expansion for the Laplace inverse transform, the inverse Z transform typically begins by expressing Fz in the rational fraction form shown below. If the proper fraction part of Fz can be decomposed into a sum of simpler partial fractions, then based on the one-to-one correspondence between sequences in the time domain and their Z-domain representations, each partial fraction can be mapped to its corresponding time domain sequence. Finally, by summing these sequences, we obtain the original sequence Fk. Depending on whether Fz is a proper fraction and on the nature of its poles, the partial fraction expansion can take several different forms. We will now discuss these cases one by one. Case 1. Fc is a proper rational fraction, meaning the degree of the denominator polynomial is higher than that of a numerator m less than n, and the denominator has no repeated roots. In this case, Fz can be decomposed into a sum of simple fractions. The coefficients Ri of each partial fraction can be calculated using the formula below, where pi are the roots of the denominator polynomial. Case 2. Fc is a proper rational fraction, meaning the degree of the denominator polynomial is higher than that of the numerator, m less than n, and the denominator has an L-order repeated pole at z equals u. Then Fc can be decomposed into two parts as shown in the formula. The first part has a denominator without repeated roots. The coefficients Ri can be calculated as in case 1. The second part contains the repeated pole, and the coefficients Qi of each partial fraction can be calculated using the formula below, where u is the root of the denominator polynomial. Case 3. Fc is an improper rational fraction, meaning the degree of the numerator is greater than that of the denominator and greater than or equal to n. First, Fc is decomposed into a polynomial in Z and a proper rational fraction. Then, the proper fraction is expanded according to case 1 or case 2, depending on the nature of its poles. Next, we will illustrate these cases with examples. Example 1. Given Fc and its region of convergence, find the inverse Z transform using the partial fraction expansion method. First, observe that Fc is a proper rational fraction. Next, examine the poles of the denominator polynomial. Z equals 4 is a first-order pole, and Z equals 2 is a second-order repeated pole, which corresponds to case 2. Following the decomposition steps in case 2, expand Fc into partial fractions. Then substitute into the formulas to calculate the coefficients a, b, and c. Next, apply the one-sided Z transform of standard sequences, or use properties of the one-sided Z transform to directly find the corresponding time domain functions. Finally, summing these sequences gives the original sequence Fk. Next, we introduce the residue method. Calculating the inverse Z transform directly using the contour integral can be cumbersome, but applying the residue theorem makes it much easier. In the definition of the inverse Z transform, the contour C encloses all isolated singularities, poles, of Fc times z to the k minus 1. Therefore, the integral can be evaluated using residues. According to the Cauchy residue theorem, the integral can be expressed as follows. Here, pi are the poles of Fc times z to the k minus 1 inside the contour C, and residential Fc times z to the k minus 1 denotes the residue of Fc times c to the k minus 1 at pi. If Fc times c to the k minus 1 has a first-order pole at z equals pi, the residue is given by formula 1. If Fc times c to the k minus 1 has an n-order pole at z equals pi, the residue is given by formula 2. Example 2. Given Fc and its region of convergence, find the inverse Z transform using the residue method. The sequence is causal. To apply the residue theorem, first identify the poles of Fc times c to the k minus 1. Clearly, the locations of these poles depend on the value of k. For k greater than or equal to 0, Fc times c to the k minus 1 has two first-order poles at z equals 1 and z equals minus 0.5. The residues of these poles can then be calculated individually using formula 1. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.